Maybe a good way to do this for attendance today is somebody who's actually watched the lecture could maybe just remind us of something we talked about so that I can catch people up, and I'll mark you down. Can you show hands people who actually watched it already? 1, 2, 3, 4. Yeah, that should get us through. And remind me your name, by the way, so I can mark you down. Yeah, so the interesting thing about quasars, so quasars are, and active galactic nuclei are kind of synonymous structures in some sense, although quasars are mainly noted because they're pointed at us, right? So they're the brightest objects. And so some galaxies seem to have really energy-intense processes happening at their core, right? More bright than our core, for instance, with these huge jets shooting out of them. And there's some debate as to whether maybe we had that in the past, or nobody really knows. Maybe we'll have it in the future. The cosmological story that we're going to start unwinding would suggest that maybe it had occurred in the past, because these are perhaps the early stages of galaxies. And what's interesting is that the reason they think they're earlier is because, of course, we run out of standard candles at some distance, and a lot of these active galactic nuclei and quasars are deemed to be really far away because they have high redshifts. But a few people have put some thorns in that model because some of these quasars, which are really quite close to us, also have high redshifts. Well, not high, but they have decent redshifts, even though the jets are pointed directly at us. So there might be some intrinsic redshifting going on there, some chemistry. We know that chemistry is capable of shifting bands, and so we don't know the answer to that yet. But I expect that story is going to change. So, by the way, while I was at this conference on the early part of the week in Minnesota, and I had a chance. I was talking with some old friends, and I was telling them about this course, and they're kind of like, well, cosmology must be a really rough course to teach right now because there's so much up in the air. And they were like, I kind of feel bad for your students, actually, because it must be terribly confusing to have a textbook that's telling one story and then you're kind of poking holes in it on the side. But I actually think it's really healthy for you guys because, in some sense, the goal of you guys all coming to college, correct me if I'm wrong, please, but you're not really here to learn what to think so much as how to think, right? Your job is to learn how to look at a problem. This is what you're going to do in whatever your career is, and you're going to have to look at it from as many angles as you can and try to come up with your own reasoning about what's going on. So I hope that's what you guys can do with all of these different narratives I'm throwing at you. I don't want to tell you that one is correct. I don't really know. I just know that there's a lot of dark matters, right? There's a lot of shadowy stuff going on that we don't know the answer to. And so I think it's a bit healthier for you to see all these perspectives. But of course, I do apologize if it's a bit unusual for a science course to not just present you with a single narrative for how things go. Fact of the matter is, when we get beyond some of these standard candles, right? Honestly, when we get past the parallax measurements, we don't directly know how far away things are, right? So we're telling these very abstracted stories, and at this point in the course, we've gotten far beyond our local cluster of galaxies, really incredible distances that are hard to imagine. And so stories that people have come up with, I want you to see them as understandable, right? I want you to understand why people came up with the stories that are perhaps on the ropes right now. But I want you to also understand that these stories change across time, and that's super healthy. As a civilization, we have to learn how to adapt, right? We might not be able to stop, the climate from changing, but we can probably adapt to it if we're flexible and we're willing to have multiple ideas in our head at once and entertain them and weigh the pros and cons of them, right? All right, cool. So thanks, Ethan. Who's next? Sophia, yeah. Yeah, that's a really good point. So let me summarize. They seem to be associated with the centers of galaxies. So that's one point I want to talk about. And then also, what processes could be driving them? The energetics don't make sense in terms of fission and fusion. So there's two interesting points to that, both of which have little caveats, right? So they do seem to be aligned with them, but then again, if we're looking at something head-on, right, and this was part of Halton Arp's argument when he was saying that there was these intrinsically redshifted jets pointed at us, is it so easy to see if you're looking at a jet on the side, right? So you have a disk, jet shooting out. okay, that's one thing. You can see where the different parts of it are. But if it's turned towards you, is it easy to separate out the background galaxy from the actual light that you're seeing in front of it, from the jet? And his argument was, no, it's not. And perhaps some of these quasars are, and he made many arguments for different quasars that seem to be associated with actually more nearby galaxies to us, in fact. And so I think there's a little bit of uncertainty about that that might not come across as to whether they are in fact associated with the galaxies that are pegged to them directly behind them. The second thing about the energetic processes, that's really interesting because the standard argument that's given for why you can't use fission or fusion is that if you had regular stars at the center of a galaxy, that they would essentially be ripping each other apart, right? Of course, this is, again, I can't keep reiterating this enough, but the only reason that people think that is because they assume the stars are balls of gas, right? If stars are not balls of gas, then they're not going to be ripping each other apart in the same way. It's more like droplets merging, actually. Which is why I brought up, I think last time, or maybe it was in the virtual lecture, the idea of these superstars, right? So there might actually be some incredible combined star structures at the center of these things as well. So again, complete bleeding edge of what's known, and we just have to keep our minds open that there might be things we haven't thought of, and any combination of these ideas could be true as well. So yeah, good stuff. Who's next? There's two other people who would listen to it. Yes. Remind me your name, by the way. Yeah, that's a really good point. So the best estimates we can get for the size of these things has to do with how long the different light on one side versus the other takes to get to us, and it's really small. It's like the size of a solar system, essentially. Perhaps smaller, actually. If you count the edge of our solar system as being the Oort cloud, it's much, much smaller. So that's on the order of a light year, maybe 2 light years for our Oort cloud. But for these quasars, we're talking light months, right? So pretty small. And that's, in some sense, another really interesting point. How are such high energetic processes happening in such a tiny space, which gets back into the idea that, it's a blank, right? And so the standard solution to that for the past 30, 40 years has been, well, physics breaks down and we have some completely exotic form of matter that's happening and so forth, or even if you could call it matter. You have a supermassive black hole. Things stop making sense. It just breaks. And so it's a really cool mystery, actually, in some sense. I don't know the answer to that yet. I don't think anybody does. Cool. And then finally, yes. Remind me your name, too. Great, yeah. I'm glad you brought it back full circle. So you bring up the possibility of galactic magnetism. Now, and I'm going to pick up at that today. I think that's a great place to move on. So, yeah, if we think about, I think a really good way of thinking about how important magnetism can be in focusing beams of light, right? Because these jets are essentially focused beams of some sort of light-emitting stuff, right? If not focus of the actual, if the core is actually just being focused like a laser or like a lensed beam of light, then you might have something going on. And it turns out that, those old TVs that probably none of you have had any experience with, those old cathode ray TVs, they do this exact process. They use magnets to actually direct. In this case, it's a beam of essentially, it would be told as a beam of electrons, but we can think about it as really just organizing these ionized atoms into a column, right? I think this is a reasonable way of thinking about it. And in that sense, you are focusing something with magnetism. And magnetism's been, I don't want to say ignored during the development of a lot of the standard theories of quasars, but it wasn't something that people were able to study until very recently. And the only way we can grip magnetism has to do with the alignment of different dust particles inside of a galaxy. And what's complicated this even worse is that the magnetism of a galaxy doesn't seem to be this nice, simple, one magnetic field, right? We have like almost these, it's That's a good way of thinking about it. It's kind of like a layer cake, right? So each ring, as you move concentrically out from the galaxy, might have an orthogonal magnetic field to the one next to it. So you can think of these like donuts inside of donuts inside of donuts. And so this has the effect of obscuring the overall picture. This is why people didn't think that magnetism was very important in galaxies for most of this time, because on balance, they seem rather weak. However, locally, you might have actually a pretty strong magnetic field. Like a single arm inside of a galaxy might, in some regions, have a magnetic field whose strength is approaching that of our own planet. And we know, at least anybody who was around last semester, hopefully has a good sense of the fact that we pretty much owe our existence to our Earth's magnetic field and how incredibly strong and wonderful it is. We'd essentially have no chance at even having had life rise up on this rock otherwise without it. It shields us from all the bad stuff that would threaten our existence. So really important, perhaps really important in focusing those beams. And of course, if you start thinking about the focusing of energy as opposed to just the, strange accumulation of a bunch of energetic processes at the center of these things, but instead you think about taking the overall light of the galaxy and focusing it, you might be closer to a more rational picture of what's going on. I don't know. This is, again, completely at the edge of what's known. So thank you guys who have already watched it. The rest of you, hopefully you can catch up and you have at least a good light background on this AGN and what's going on. So today I'm going to tie up as many loose ends as I can about the standard picture of the metamorphosis of the universe. The standard picture is, of course, that the galaxies all form, it's a linear story, right? So we'll get into the Big Bang, but of course you're probably all familiar with this basic idea that the universe was born, right? And born from what? This is anybody's idea, but it was born, and that it evolved, or I think metamorphosized is probably a better term, because evolution is usually a population level thing, right? But in this case, it's sort of metamorphosized like a butterfly from one form into the next. So all the galaxies were more, or let's say, what we would end up with for all of our galaxies started at once. They may have changed shape as they merged and collided and dissipated, but what we're left with is the leftovers of this initial event. And so it's this long unfolding. And so today, a big part of that story is going to come down to this idea of the cosmological principle. Does anybody know what the cosmological principle is? All right. Yeah. Yeah. Yeah, isotropic. Yeah, nice. Very good. So what does that mean? So here's the truth of the matter. When we take a telescope like say the Hubble, right? It seems like most of your textbook was compiled during the years of the Hubble telescope, which was kind of the predecessor to this James Webb business. Well, they could only really use it in a dark spot, right? So they plop the thing at a nice Lagrange point, right, where it can the satellite can sit gravitationally unaffected. It'll stay in the same place with respect to the Earth as we go around the sun. Now, that only gives them a window into one little, I think it's less than a percentage of the sky, right? And so when we look out and make these really long-range decisions about what's happening, or observations about what's happening in the universe, what we have to do is apply that tiny little percentage to everything, right? In order to make a cosmological discussion that is about the entire universe, we have to use our tiny little window and extrapolate it onto everything. And so the entire basis of cosmology, of scientific cosmology, is hinging on this cosmological principle that what we see in one place of the sky is true for all of the sky. And so that assumption is essentially, like you said, that it's homogeneous, that the universe is homogeneous. That is, basically, there's same density of stuff everywhere. And secondly, that it's isotropic, right? So that means that what's happening in one place is symmetric to what's happening in the other. And, this is a really hefty assumption, and I think that if we understand why people had to make that assumption, it makes more sense why we end up with the cosmology that has brought us up to this point. Unfortunately, like much of these other things that we're going to investigate about the standard cosmology, there are some issues with it. In fact, and we'll get to this at the very end today, hopefully, there appears to be quite a bit of what we would call anisotropy, so the opposite of isotropy. This is basically clumpy stuff everywhere, different balances, different asymmetries in the distribution of matter. And which is beautiful, actually, in that we're starting to see these structures, right? It's not just galaxies forming into clusters, but the clusters of galaxies are formed into these long spider-webbing filaments, right? There's some sort of wide-scale structure going on here, which is really exciting. But of course, it sort of plays havoc with the cosmological principle that things are kind of the same everywhere and equally distributed. It doesn't seem to be the case. So this is going to be a huge part, and we'll look at the different reasons that people believed that originally and sort of the new evidence coming out. All right. All right, let me make sure that I've wrapped up everything that I wanted to say. This is a pretty good review. One thing, I guess, there's one more story I want to tell you guys about mysterious matters, let's say. We have this problem, right? There's these very active galactic nuclei. We can't think of the energetic processes that would afford them, at least not using ideal gas laws, which then leads us to a black hole, right? And a black hole is an interesting piece of verbiage, actually, because it means very different things to different astrophysicists. Some mathematical astrophysicists might think of it as being defined by this singularity. And can somebody remind me what a singularity is exactly? Yes. More broadly, not just in the context of the. Yeah. So if you have a mathematical model, a singularity is generally a place where you reach an infinity in your equation, right? Now these have happened before in physics too. So I told you guys before the story of the ultraviolet catastrophe. Does anybody remember that one? It's a little bit complex, but essentially when they were studying heated bodies and the spectrum that they gave off, the equations that they used to describe the slope of those frequencies and the curve that fit, how much intensity of different frequencies would show up, it gave a singularity, which was the fact that the energy should go to infinity according to the classical model of light production as you get to smaller and smaller wavelengths. So the blue and the ultraviolet, essentially these bodies should be giving infinite quantities of ultraviolet light. Now, they had the measurement abilities at the time to realize that this wasn't actually happening. And so this was in some sense an easy singularity to dispatch with, because all they needed to do, and not to belittle it, but through some incredible actually acts of mathematics and reasoning, they invented the photon, right? They realized that light wouldn't be continuously emitted at all frequencies, but only discrete frequencies, right? So you need a full wave to have light. You can't have like a little bit of a wave. You need a discrete wave. Light is always a back and forth depolarization. So they invented the photon, they had a new equation, and it fit the black body curves perfectly. So that's like a very famous singularity that disappeared. There's one more I wanted to tell you guys about, just to sort of show you how these things go, because I think that these singularities that we're talking about in black holes will probably also go the way of the dinosaurs, but we haven't got that leap, right? We haven't invented the photon or come up with the solution to it yet. The other one that's really interesting is heat. So well, you guys, I'm almost certain you haven't heard this story, but all the way up into the 1800s, people thought about heat as a fluid, right? It was, And there's a deep history of magical fluids in physics, and I would say electricity is kind of the last one that we're dealing with today. But people thought about heat as a fluid that was transferred. So, when you put a hot body, some sort of like, a heated metal next to another metal, it would transfer the heat into the one that it was touching, right? And they created all of these thermodynamic laws based on this flow concept. And we still talk about heat flow, right? You'll hear that all the time. That's because the basic differential equations that give you the dynamics for how thermodynamics operates, how essentially to construct an engine that's efficient, they all work perfectly well if you treat heat like a massless fluid, right? And so the entire scientific community was completely convinced that heat was a very much like dark matter or something like black holes, that it was just let's say, an imponderable fluid. You couldn't touch it, it didn't have mass, but it flowed, right? So it must be a fluid. Now, somebody made the really interesting, and I don't remember who it was, made the really interesting observation. There was a lot of gnarly wars going on back in the, do you know who it was? Do you remember his name? Figure it out. This is my lovely wife, by the way. The lovely Dr. Benderbury to the rescue. So there was a lot, cannons were big business back in the 1800s, as you can imagine, sort of like drones are big business today. They were boring these cannons. So the way they would do it is they would forge this big column of iron or whatever the heck they made them out of, some sort of metal. And then they would drill out the center so that you could put a cannonball in it, right? And somebody who was very interested in mechanistic science was privy to this process and had the sensibility to recognize that, it's kind of strange that when we drill out these cannon holes, we generate heat. But what's really weird is that we never seem to run out of it. So as long as I keep my drill bit spinning, the cannon seems to be completely unemptyable. Like I could drill away all of the cannon and I would still have heat left over. In other words, there's an inexhaustible supply of this fluid inside of the cannon, right? And this, I think, started to really break people's brains because in some sense, just like these different contradictions that I'm bringing up in this course cosmologically, they start to pile up to a point that they just make people kind of nauseous, right? They're like, you know what, this just doesn't feel right. This is just starting to be an untenable physical explanation for what's going on. How can we have an infinite supply of a fluid, right? So on the backs of that, scientists started working really hard to come up with an alternative explanation. And I think this is what people are doing today in the cosmological community. And the idea for what actually heat was a very similar solution to the photon solution to the other singularity I was talking about with the ultraviolet catastrophe. The idea that solved it was that heat was actually the motion of the molecules involved in whatever material you were looking at, right? So that was called the kinetic theory of gases. Count Rumford, and is Count Rumford, does he have another name? Count Rumford. These guys all had different names. It's really interesting. There's Lord Kelvin, who had a different name as well. They're all barons. It's a very strange time. It's hard to imagine. Okay, so Count Rumford made this discovery. But needless to say, Boltzmann actually was a mathematician who came along and actually realized that if he made a discrete unit, right, an actual amount of energy that an atom could vibrate with, scaled by its actual temperature, how much vibration was possible, then all of a sudden you had a working model for what heat was that didn't require it to be this infinite supply of fluids, right? And so I think this same process is playing out with electricity today. And we've sort of poked at it a little bit along the way, but if you ever have the will to go down the rabbit hole of trying to figure out exactly what electricity is, you'll very quickly find out that it's not so simple as what you learn in high school, that there's a bunch of little electron bowling balls like flowing like a river down a corridor or down a conduit, right? That doesn't seem to make sense. The actual change in that charge isn't equivalent. In other words, the speed of those electrons isn't as fast as the actual action of the electricity. There's a similar story playing out right now with respect to electricity. So anyways, these are two different singularities that have gone the way of the dinosaurs in fairly recent times. And so I think when we're left with these puzzles, like these active galactic nuclei, and we say, well, there's a singularity at the heart of it, that should be the first sign that, hey, there's some work to be done here. And there's some sort of brilliant revelation as to what's actually occurring. And so our placeholder, of course, is a supermassive black hole. Now, I wanted to read you guys a little quote here from John Locke, actually. This is a fantastic book. If any of you are interested in, it's called Language in Thought and Action by, well, I don't know if these guys are, I think it's a father and son team, actually, the Hayakawas. Fantastic book, and it really gets into thinking of humans as being defined by our ability to talk, and this idea that, you know, we don't just wake up one day and, you know, derive the world for ourselves, right? We're given information, and that our entire civilization and our entire human experience is in some sense mimetic, right? We're given ideas. The ideas have a life of their own, and we inherit them, and language is at the core of what makes us human. So one of the prefaces to a chapter in this book, he has this Locke quote. By the way, anybody know who John Locke is? Yeah. Locke was an English physician, actually, but he's probably most well known as a philosopher. But Locke's philosophy was sort of at the base of this country, honestly. We have him to thank for the Declaration of Independence and all of this. He was really one of the first people to suggest that there's inalienable rights that human beings possess, and that to anything that deprives humans of their innate rights is tyrannical and deserves to be displaced, which is pretty radical and pretty awesome, actually. But Locke wrote this interesting point, which I think is really, really salient in terms of this discussion of why it is that these mysteries get sort of plastered over and treated as if they're solutions. He writes, "Vague and insignificant forms of speech and abusive language have so long passed for mysteries of science, and hard or misapplied words with little or no meaning have, by prescription, such a right to be mistaken for deep learning and height of speculation, that it will not be easy to persuade either those who speak or those who hear them. But they are the covers of ignorance and hindrance of true knowledge." So it's very, very easy to take a problem and technologicize it, right? To put it in such highly technical language or such obscure language that it can be treated as if it's a solution. And this is, I think, one of the biggest problems we have at each stage in this scientific journey, is thinking that our problem is actually a solution and we can just move on. And this is just going to become more and more apparent. By the time that I finish this story of the large-scale structure of the universe, I mean, we're sitting with something like 90%, 97% mystery and 3% that makes sense, right? So this is, I hope this isn't disturbing, but I hope it's inspiring that there's a lot left to be done when it comes to making sense of things. So at the moment, we're working towards this story where we actually explain the evolution of these large structures and so forth based on what we would call dark matter. Now, dark matter is not really a solution. It's actually a problem, right? It actually is a place where the theories stop making sense. But we need 97% of the mass of the universe to be present when it isn't in order to make these theories work. So, pretty cool, pretty exciting. I just think it's worth everybody walking out of here understanding that humans do this thing, especially highly technical professionals do this thing, where, you know, this is actually really present in medical industry all the time too. You know, you'll go to the doctor and you'll be like, I'm feeling sick or whatever, I got this problem, and the doctor will give you a very technical diagnosis maybe at the end of the day, and you'll be like, great, now what can you do for me? And they're like, nothing actually. Like, we can't really help you. So it happens, and it happens in all sorts of disciplines. It's very easy for us to think that by putting a name on something that's going to move us forward. And sometimes it does make the problem focused, but sometimes it allows us to sort of sweep it under the rug. So we have to be careful about that. You know, in general, as we go back through the history of astronomy, things have always been further away than we think they are. So remember the story of the Milky Way being the entire universe until really the 1920s. Two, things always tend to be way older than we think they are. So all the way up into the 19th century, people had strong convictions that the Earth, there was a strong scientific majority that believed that the Earth was somewhere on the order of 6,000 years old. That was less than 200 years ago, okay? Three, our theories often tend to smooth over complexities that emerge and change our understanding. A good example of this that we talked about was the Cephids, right? They used these Cephids, these blinking stars, as standard candles. And it turned out that the Cephids were later found about 30 years later to actually be comprised of two different kinds of Cephids that had different distances, and this actually forced us to redraw the distance map by a factor of 2x at that point. That was in 1950. I believe it was Walter Beatty who came up with that. And then four, when we see this word dark and black, it usually means that there's something we're missing. This is a mystery. So we put all these things together, and we have to start thinking about ourselves as scientists. Our job is to sort of root out these monsters in the room, right? When we talked about, I spent a whole lecture talking about the myth of Andromeda and Perseus, right? Which I think is such a repository of wisdom with respect to how our whole lives go as human beings and how this affair of science proceeds too, where there's a monster terrorizing our town. In this case, we have these dark matter, we have black holes that are sort of terrorizing our physics, right? And we have one of two options, right? We can sort of be like, this is just our lot. We can, and it continues to, burn down our coastline. We can sacrifice our daughter to the monster, like Cassiopeia did, right? With Andromeda, tie her to the rocks, and just hope that will appease things. Or we can really take those dragons head on, right? And do what Perseus did and come back and slay the monster. The interesting thing I kind of skipped over when we told that story about Perseus is that he actually, in order to kill that monster at the end of the day, how did he do it? Well, he killed another monster who was Medusa. He took Medusa's head and used Medusa's head to turn that monster, the sea monster, into stone and rescue the princess. And I think that's also really interesting. Oftentimes you have to beat these things in stages, right? It's almost like one of these long role-playing video games where you have to, gain up the experience and build up the armor and move forward, right? It might take us understanding something simple like the basis of our own sun, right? The material basis of our own sun, in order to actually address these bigger problems. We might not be able to take them head on with the tools that we have available to us now. We might have to go back and actually build up that armor across the entire history of the sciences. So, and it's gonna be difficult too, because if we look back across the history of science, textbook talks about Giordano Bruno, who was burned at the stake, according to your textbook, for saying that other worlds existed, right? Other planetary systems and so forth. He actually kind of made enemies of the church for a lot of reasons, actually. But it's interesting that your textbook even highlights that, because what they're pointing to is that you have an authority, a cosmological authority, who is so dead set on preserving the mysteries of their own esoteric cosmology that they're willing to kill people over it, essentially. And you might think like, well, that would never happen today. And it's like, yeah, you're probably right. Nobody's going to get burned in front of 300,000 people for denying the standard authoritarian picture of the cosmos, but you might not have a happy place in a university. You might not be able to get grants, right, to study something outside of that. And so these things do kind of happen. So what's the other option? The other option is that you just make sense of it, right? That you have to actually examine these problems with an open mind, look at the possibilities, look at what doesn't make sense, and put those things centered. Have those be a big part of the discussion. I think one thing that's happening in the world right now that's really exciting for your generation is that there's the central authority. If we can think about the university structure as being analogous to the church in Bruno's time, right? The scientific authority comes from not the church today, but from the university. So the biggest bosses at MIT and Harvard and Stanford are the ones who give us the standard narratives that are repeated by all of the different pop sci magazines, the New York Times, and everybody else, right? But what's really interesting today is that more and more people are actually becoming intellectually curious, and not through university structures necessarily. There's a lot of public discourse happening, more so than ever in the history of the world, on places like Reddit, YouTube, right? Discord, independent publishing outside, right? There's a lot. And this is, of course, made a little bit of a mess because, anybody can say anything and write anything. So you actually have to be able to, in this age that we find ourselves in, the skills of being able to actually learn how to think about things and not what to think becomes more and more important than perhaps ever before, because all of these discussions are happening simultaneously. And the academic narratives with respect to something like cosmology leaves us really scratching our heads, because we come to the answer being that there's a magical substance that accounts for everything we see. And if that's, for whatever reason, untenable to you, there's a lot of people with alternative discussions going on about what that could be. Some of them are terrible. Some of them are just replace it with another magical fluid. But we have this moment right now that's more fertile, I think, than ever before. I think it's, in some sense, this internet that we've created is very much like the printing press, right? This is the first time that people can actually exchange ideas en masse. And there's going to be, and I think there is going to be a huge contingent of ideas coming not from this place, right? Not necessarily coming from universities, but also coming from outside of universities. And that's going to be kind of painful. I think that the policing of information is going to be a huge part of that battle for the first couple decades. But people really tried to, the authorities, the churches, and the kings, the royalty tried really hard to police those books at first too. And of course that turned out to be completely untenable. It's just, how can you stop people from sharing ideas? You can't. They'll always find a way around it. So, a really beautiful age, I think, that we're entering into as far as information and intellectual freedom, the ability for each of us to make sense of what's happening. But we have to take on that burden, right? We gotta be willing to fight those monsters ourselves. We have to be willing to trust that we can think, that we can find different pieces of information and slot them into something that's rational to us, that has a story that makes sense. And so I think we've never been less dependent on intellectual authorities to tell us what to think than we are today. We at least have the means to go around that, which is pretty exciting. All right. We pretty much covered galactic magnetic fields in the pre-class discussion today. I did want to direct you guys. My wife and I actually had a really long and wonderful conversation with this guy. He's a Stanford astronomer who's studying galactic magnetic fields. He's one of the first people who's really been publishing heavily on this topic. And so we had a nice 3-hour conversation with him. If any of you are interested and don't want to dig into, I actually showed you guys a textbook that's pretty good at the end of the virtual lecture. But this is a cool podcast where we explore a lot of these ideas and talk about how galaxies might be, in some sense, organized, not just the AGN, but the galaxy structures themselves. How is it that they look the way they do? Can we maybe get around this galactic rotation cohesion problem with some magnetism introduced? Maybe. So check that out if you want. I think I put a link in Moodle too, but you can just find it if you Google it. All right, so now we get to back to the standard story. So the standard story, of course, galaxies, there was a birth of everything. The galaxies have essentially been nucleated at the very earliest days, and that they've been evolving since then. They've been combining, ripped apart, things like this. It's interesting, so the textbook actually has this quote: "We've observed galaxies so far away that we're seeing them as they were when light left them more than 10 billion years ago." Now, that must be a really outdated statement, which is surprising to me because this textbook can update in real time. The truth of the matter is that with the new telescope, I think that was probably a Hubble statement. The new telescope has seen these galaxies going all the way back to, a matter of millions of years after this supposed moment of the birth of everything. And when this happened, there was a number of headlines in the pop sci that were sort of troubled by this, right? Galaxies shockingly similar to our own found near the beginning of the universe by NASA. And indeed they were, right? And I think what was really disturbing, and that's why telling this standard narrative of this linear evolution of galaxies is a little bit difficult to pull out of my mouth, because the fact of the matter is that a lot of these galaxies that have been observed seem to be more or less evolutionarily synced up, let's say. They look the same as the galaxies that are supposed to be billions and billions and billions of years old of evolution, right? So, I think this has been perhaps one of the most troubling years in the history of cosmology and astrophysics, because on one hand, there's a lot of people taking potshots at the cosmologists like, what this story you've been telling us for 50 years doesn't make sense. And of course, I feel bad for them because they're like, well, hold on now, we don't know, this is just a few data points we have, we don't know what's going on. They really haven't had time to construct an alternative story for what's happening here. And so it's a bit of a painful moment, I think, inside of the academy for people who are working on these models. Right when these reports started coming back, people were saying, well, maybe we haven't calibrated the data right, maybe, something's not right with the instrumentation, and this didn't prove out, right? So over the subsequent year or two, I think it's been about 2 years now, maybe, the calibrations have been, let's see, fortified and checked. And indeed, we are looking at galaxies from a moment where the standard model would have predicted that not only did we not have galaxies, but the stars that we had would be very homogeneous and simple, and it just doesn't seem to be the case, right? So a lot of the cosmologists now are sort of scrambling to come up with models for how these galaxies could have formed really, really fast. So how fast? 300 million years fast. Now, let's think about this for a second. Our Earth has had life on it, as far as we can tell, for at least 3 billion years. That's 3,000 million years. And so how an entire galaxy could form in a fraction of that, let's say a tenth of that time, with all of its stars and all of its solar systems and everything fully intact, it really, really stretches the imagination. But unfortunately, without a new cosmological model to replace the old one, the best thing that people can do is try to put Band-Aids on the old one. And so there's a lot of that going on right now. How can we speed up these processes? How can we come up with gravitational evolutions using general relativity for how the universe could go from, a singularity, a nothingness, into something so complex as an entire galaxy in a matter of a few 100 million years? From when I first started reading about this stuff, I was reading all these popular physics books, and I was probably 12 or 13, and I was trying to understand some of these things, like black holes and the Big Bang and stuff like that, and I really, really was hoping somebody would give me a coherent story for how it is that something comes from nothing, right? And I've never been able to satisfy myself with that to this day. How it is that you essentially, because it seems like you go into a science classroom on your first day in 7th grade or something. One of the first things you'll learn is that, stuff, right, matter, is never created or destroyed, actually. So you might make atoms, but you need other atoms to make new atoms. And so this has always been a really, really interesting question for me. And what's interesting about it is that if you can't make sense, if you can't rationalize how something can be created from nothing, then as ugly as it might be, the default to that, the assumption you have to make is that that stuff's always been here. Because if you can't come up with an actual mechanism, right, a cause and effect story for how something comes from nothing, then you're left with the fact that it doesn't, and that it's always been here, which essentially takes us full cycle back 200 years before today, where many of the scientists treated the universe as an eternal structure, that it was always here. It was changing shapes, but there's nothing that comes into being, and there's nothing that goes out of being on balance. And so it's interesting how this goes full cycle. I mean, there's a similar story with the solar system itself. For any of you who were in the class last semester, we were talking about how Kant came up with this idea, essentially, of how the solar system formed out of this collapsing cloud of debris and so forth, and started spinning as a result of the angular momentum contraction and all of that. And people tried for 300 years to come up with better ideas. They're like, this philosopher, what does he know? And they couldn't do it, right? So there was all sorts of different models involved. And back in the 1980s, a Russian scientist actually came along and said, you know what? Kant's model's fine, and I've done all the mathematics to show how this is actually possible. And here we go. We essentially have this nebular collapse thing for both galaxies and for solar systems at this point. So sometimes ideas in science come, they die, they come back again. And I wonder if that's not what's happening. There's also the possibility that, well, maybe somebody just hasn't figured out the mechanism by which something comes from nothing, or maybe the universe was in some more isotropic, like crystalline state. Instead of nothing, it was just the stuff was just very still, and then it was set into motion, and that's essentially what the birth of the universe was. Again, this makes for the really painful necessity for what set it into motion. What was the cause of that motion? Because one of the primary laws of thermodynamics is essentially that motion never really dissipates. It just transfers from one body to the next, right? You can't get rid of motion in a closed system. So there's people working on that. I met with this cosmologist at, I think it was the University of Ottawa. And he's made a proposal that made some headlines too, where he said, okay, well, we can solve this problem of these galaxies if we just set the birthday for the universe back about it's twice as old as we thought it was, right? And he does the, let's say, relativistic calculations of how that would allow for the production of these galaxies, using basically the same story that the textbook gives, this slow metamorphosis, but you just have a lot more time for it now, right? And he says, well, the Hubble expansion is, this redshift relationship, isn't actually accurate because the light is losing energy as it travels across these vast reaches. So it's a sort of tired light argument to move the birthday back. And that might be the case. I truly don't know. Again, there's no mechanism given, so it's a bit dissatisfying for me how this first action occurs, right? But this is what I think we should expect to see. We should expect to see steps being taken in the direction of making sense of it, even if they're not wholly addressing the issue. So that's an interesting conversation too, if you want to check it out. I can't recall his name off the top of my head. All right, so this kind of brings us up to the standard cosmology, which we've been dancing around. The standard cosmology assumes that the distance to these farthest galaxies is a result of the redshift. The redshift tells us how far away they are, and that the redshift is sort of exponentially increasing because the universe itself is expanding. And what they really mean by that is that space is expanding, and if space is the distance between bodies, then the distance between all these bodies is increasing, which is very strange. Now, in order to make that expansion make sense, the entire cosmology is built on the back of Einstein's relativity, right? This is the fantastically accurate model we have to predict how bodies move with respect to each other. But the annoying thing for everybody is that relativity only talks about gravity as being the primary actor here, right? And if you want gravity to accomplish all of that expansion for you, well, it means you have to have a lot of stuff that we can't see. And I mean a lot of stuff, right? So the standard cosmology is called lambda cold dark matter, LCDM. The idea is that ordinary stuff, atoms, accounts for only 4% of the gravity that would be necessary to explain this expansion business. The letter lambda represents the cosmological constant, and that's the coefficient for how much expansion is happening, given circumstances, observations. Now, the cosmological constant, of course, draws heavily on this exotic material, right? Dark energy, dark matter, stuff we can't see, in order to give us an accelerating expansion of space that isn't completely that counteracts gravity, right? So it's like, in some sense, if we just assumed that gravity was the only player in the world, it'd be very difficult for us to understand why the bodies, right? We have this story about gas atoms pulling themselves and collapsing down and making a star. The natural question is, why in the world doesn't the whole universe do that? Why doesn't everything just pull itself into a big knot, right? And why don't we have sort of the opposite of a Big Bang, like a big crunch? And the answer to that is that there's a magical force that's pushing them all apart. And this is where we get the concept of dark energy. And don't worry, I'll get more into that later. So I think a huge part of this is going to come down to understanding light better. I think that all we have is light in astronomy. And if we are saying that the redshift means this expansion without a doubt, or redshift means the Doppler recession of something without a doubt, and then we run into these contradictions, such as I've pointed out today, a good place to start might be really going back to the drawing board of what in the heck is light, right? Because if we don't have an actual model of what one atom is doing to the other one physically, materially, in order to affect the observation, the measurement we call light, then how in the world are we going to be able to deduce what this light actually means, especially at such extraordinary scales of billions and billions of light years away from us? So I have a sense that some of this reckoning may come down to very fundamental reconsiderations of this idea. Planck, like I said at the beginning of the lecture, gave us this brilliant insight that light had to be discrete units, right? And Einstein actually got his Nobel Prize for elaborating on this idea. It was called the photoelectric effect. But that the photon was a thing. It was actually an occurrence. There was this discrete unit. Now, it's strange that the photon was very quickly treated, okay, great, we have discrete units of light. It's very quickly converted into a solution by itself, but there's a lot more questions to ask there. Like, the photon is basically treated as a magical particle at this point, right? It's massless, it doesn't interact with itself, so I can take two laser pointers and cross them, and I don't get a pile of photons on the floor. But it has push to it, so it has momentum, and just some basic physics will tell you that momentum, and you calculate momentum, has a mass component to it. So how do we rectify that? It's very strange. Well, perhaps if we start thinking about light as actual interactions with atoms that are actually interacting with their neighbors and relaying that push, that genuine physical push and pull with one another across vast relay networks, we might get closer to a solution set. It loops us back to the idea of what is a particle in physics. It's not the same as a particle in chemistry, right? It's not the same as a mote of dust or something like that. A particle is just a reproducible, predictable measurement of some phenomenon, right? It's even described as sort of the solution or the collapse of a more probabilistic function. It's like when we measure something, how much energy do we have at this point? How is that motion being conducted? How does it move? How is it deflected? How can we change the beam of that energy or that radiation with magnets, right? So light is probably the biggest mystery at the heart, and probably contains, once we have a more rational conception of what light is with respect to how atoms are actually conversing with each other, we might have a better idea of how all of this redshift business plays out, and why our idea that space is expanding might not be the best way of looking at things. Okay. So one thing that's been really important is trying to understand how it is that some of the galaxies, why the galaxies look different from each other. And a huge part of that has evolved in recent years is the idea that galaxies actually merge with one another, and that you can actually produce these bulges, these huge agglomerations of material at the center of galaxies by slamming different galaxies into each other. So you get all sorts of, basically every structure that we see that's not a standard spiral galaxy is explained by way of a merger at this point, right? So everything from these tendrils of stars and gas, the ring structures, even the central bulges are explained by mergers. Even these elliptical or irregular galaxies that don't have a nice spiral shape, they're explained as being the mergers of basic, simple spiral galaxies, like the ones that we see, that we've shown to this point. Now, that does make a lot of sense. So these are some really beautiful images of different galaxies that appear to be interacting in various ways. The question is this a one-time affair, or is this something that's continually happening, right? We've talked about how the Andromeda Galaxy is just closing in on us at a really high click, and actually in a matter of a few billion years, it should be smashing into our own galaxy, which will turn us into something more like a elliptical or a irregularly shaped galaxy. So another thing that this has been used to explain is that when you smash two galaxies into each other, you actually have the opportunity to create a lot of new stars. So if we look out and we see a galaxy that has a huge, fairly lockstep timed population of really young stars, the solution set is that these galaxies must have slammed into each other. Two galaxies must have slammed into each other. Maybe so. They call these things starbursts, by the way, which reminded me a bit of this, these cupcakes that Bo made. Some beautiful merging galaxies. AGN's also thought to be perhaps the result of the mergers of different galaxies. One thing I didn't mention last time. Now, this brings us sort of up to the cosmological principle. And I think that we did a good job of reviewing what the cosmological principle was. Now, the cosmological principle was held rather strongly for the early years of using telescopes, and all the way kind of up into the 80s and 90s. Actually, one of the reasons that people really stood by this cosmological effect was the discovery of this microwave background radiation in the 1960s. And so, if you look at this map of the CMB, which you probably, I don't know how you would have avoided having seen this somewhere in popular science up to this point. The argument being that it is fairly homogeneous and isotropic. Now, this is technically an anisotropy map because it shows hot and cold spots, but the fluctuation is really, really tiny in terms of temperature. And the basic idea is that the fluctuations are more or less random everywhere. And so when we look for this signal, this hum, which was very quickly attributed to the birth of the universe, essentially in the same year it was discovered, when we go and we look for it, we see this very nice, even, fairly chaotic map of the background. And this reinforced the cosmological principle that allowed people to think, well, okay, things are basically the same in all directions. Now, I am going to leave for next Tuesday a bigger discussion of the CMB, because I think there's a really, really interesting story going on with respect to this CMB. But what's really interesting is this map was taken by a satellite that was orbiting away from the Earth. It's called the WMAP project. And what the satellite did was, well, the CMB was actually detected on Earth. And later it was reinforced by satellites in low Earth orbit, right up in the sky, maybe 60 kilometers above us. What they did was they actually took the frequency that they were looking at the temperature they were looking at, and what they did was they had two measurement devices that went looking for this signature in both directions of the sky. And then they subtracted those amounts from each other, and this is the map that they made as a result of it. Now, it's an interesting project that I want to get into next time about having a frequency that you're hoping to find and then going and looking for it. Because the truth of the matter is, if you took any frequency that you could just pull a number out of a hat, you could also do the same experiment and you'd probably generate a map very much like this. But more importantly, this is what the map actually looked like when they took it, right? So this is, of course, an extraordinarily anisotropic map, right? You see large differences in temperature on both sides of this field, pretty significant, right, in both directions. Now, what they thought was, okay, well, this is due essentially to the motions and, well, essentially to the galaxy itself, right, to the Milky Way, is getting in our way. And so if we make the assumptions about the temperature and the motion of the Milky Way, we can subtract all of this garbage. And if we get rid of this really dominant signal, then we're left with that nice isotropic map that we saw this guy from before. So that's a huge amount of data subtraction, first of all, to get that map, which maybe would be a red flag in any other discipline. But what's really interesting is that there's some serious homogeneity violations with respect to the way that this asymmetry appears, actually. So when people actually compare these motions, right? So the idea is we can subtract all of this bright noise and get a good map of the CMB by subtracting the galactic motions and so forth. The problem is that when we look at the motions of something like the type 1 supernovas that we talked about earlier, or the quasars that are distant beyond our galaxy, the motions that we have to use to subtract this aren't the same motions that we have with respect to those other galaxies. There's also some portion of the Earth's solar system motion which doesn't seem to agree with the motion that's being subtracted. So let me try to summarize this for you. The assumption, in order to generate this nice isotropic cosmological principle supporting map, is that you can subtract the motion of the solar system and the galaxy from the CMB measurement in order to get this map. The problem is that the subtractions are not the same motions that we seem to have with respect to some of the other objects, both locally in our galaxy and outside of our galaxy. So this is a huge thorn. I think this has actually been given a name. It's called in cosmology, this problem is actually called the axis of evil, which is pretty funny. That there's some sort of correlation between the plane of our solar system, the rotation of galaxies, and some aspects of the motion of the CMB. So it seems like there's something local actually affecting the way that we read the CMB. And that's really disturbing to the idea that this is actually a cosmological signature at all, that it has anything to do with the widespread universe, or if it's something coming from very nearby. And the only experiment that's been done to look at the thing away from Earth is one that assumes the CMB has a particular frequency and then goes looking for it. I keep meaning to do this experiment for you guys. I wish I could think of an easy, simple way to do this, but you know, I work with synthesizers a lot. I'm really into music, and if you take a white noise generator on a synthesizer and just turn it on, it's just and then what you do is you pick a frequency and you put really tight band frequency. You just sweep the frequency sweep the range, right? I can just pick out maybe 1,000 hertz, and I tighten it up so I'm only listening for 1,000 hertz. Well, what's it sound like? It sounds like a tone. It's just like, wee, right? And I can find any single tone that I want. I can literally make a musical instrument out of white noise by selecting for a note and sampling it from each tone that I want in the series. So it's very easy to pull out a picture of anything once you know what you're looking for it. And they found the actual frequency spectrum and the temperature of that thing very, very close to Earth. It was actually discovered on the coast of New Jersey, and then later replicated, like I said, in balloons and so forth at atmosphere. So this is a really interesting struggle with respect to the cosmological principle. And it seems to be followed up by the widespread structure of the universe. So not only do the galaxies seem to organize into clusters, and this is a sort of chaotic diagram, but it shows how the various galaxies seem to be bunched up together in our local neighborhood. But what's worse is that, I'm going to skip some of this. What's worse is that these structures actually seem to be organized into deep filaments with respect to one another. Here's another reconstruction of the filaments. And I think this is actually one of the most exciting things in all of astrophysics right now. I mean, these are really, really beautifully organized structures, right? They almost look like neurons or something, little dendritic structures, right? And of course, the idea is that these things formed across time. But ignoring that, what we have is the appearance of some really, really deep inhomogeneity in the universe, right? There's stuff in some places, and there's complete absence of stuff in other places. And we can't do that with gravity alone, because gravity alone would just have it all turn into one big swirling mess at the center. So in order to make this evolution happen from a completely homogeneous universe after the Big Bang to these very beautiful structures, we have to, of course, invent this magical fluid that pulls everything out of the voids and so forth, right? So we're left with this picture that, 4 to 5% of our universe is normal stuff. Something like 30% of it is this really cold, dark matter with no signature, this magical fluid. And then there's this dark energy, right, which is responsible for counteracting gravity. And that's the story that we're left with respect to our standard cosmology. So at this point in the course, we're going to examine the pillars of the Big Bang, and we've covered one of them, I think, fairly robustly, although I want to make sure I could get all the details in, which is the redshift, the expansion idea. The second pillar is that cosmic microwave background radiation, and I think there's a really, really interesting story to be told there as to what is actually going on. Now, one of the biggest, I think, reasons to suspect that all is not right between these two pillars of evidence is that they don't agree with one another. So when we actually try to calculate the expansion rate of the universe, we get two very different values for the CMB. It will tell us the motion of this primordial goo. And if we trace that back to an origin point, we get one birthday for the universe. If we use the expansion rate based on redshifts, we get a different birthday. Now, you might think, okay, well, that's just, error measurement. The problem is that those error bars are really, really tight on both those measurements. And in fact, the standard deviation separating them, right? So how much fuzziness for each one of those measurements is plausible given the measurement techniques is completely separate. So those two curves are both really reliable in terms of the way that they're mathematically interpreted, but they don't overlap at all by something like, I don't want to say off the top of my head, but more than one standard deviation. I think on the order of like 10 standard deviations. Very, very big. So these two models are both the pillars for this story of the birthday of the universe, but they're also in contradiction with one another. And so our job is, in some sense, to try to perhaps make sense of these two pillars in other means as well. And we've talked a bit about the redshift and the idea that people have tried on these tired light explanations over the years, and nobody's really succeeded with it. And there's not too much more to say about that. However, the CMB is a really, really interesting story. And so next time, I'm going to take the luxury of time to actually walk you through the discovery of the CMB, talk about how quickly it was turned from an observation into a sort of theory of everything and reinforced this idea. Remember, I think we mentioned it already, the Big Bang was essentially invented by this Belgian priest, right? And of course, the Pope loved it because it gave, in some sense, the church a bit more authority all of a sudden because they had a scientific version of this creation story. And actually, Lemaitre, the Belgian mathematician priest, had to sort of tell the Pope to pipe down a little bit because he was making him look bad and not scientific, right? So it wasn't really taken seriously as science, honestly, until the discovery of the CMB. And so that's a really interesting moment where that conversion happens. And it's one of the first moments where the widespread scientific community goes from having this picture of an eternal universe to something that was finite and more close to traditional mythological conceptions of the universe. So, look, we got all these monsters in the room, and I can't necessarily tell you what the answer is, and I don't think anybody can. I can't tell you what to think about all of these monsters. I can only tell you there's monsters there, and that if we, put our minds together and reach far and wide and keep the conversation open, we might actually come up with some pretty brilliant solutions to this. But what we do know is that we're probably subject to all of those errors that we've made in the past concerning how limited we often make these conceptions, right? The universe is almost always bigger than we think it is. It's almost always been around longer than we thought it was. It's almost always more, these mathematical formulations for things are almost always more complex than we thought they were originally. And so I think we should expect all of those same things to play out with respect to this story, which appears to, have quite a bit of gremlins crawling around beneath the floorboards. So let's put a pin in it, and we will look into the CMB with the luxury of depth next time. And I hope you guys have a wonderful weekend. It's our last week of class, sadly, next week. Please do be thinking about your creativity projects, your final projects. Let me know if you have any questions about that stuff. The things I've seen so far, really good. And yeah, I'll be looking forward to our last week. Have a good weekend, guys.